Good morning. So today I'm going to start covering Chapter 5 on CPU scheduling. This is a pretty comprehensive chapter, and it covers both a lot of different scheduling techniques, including real-time scheduling, as well as some case studies. So we'll see how things go on the case study part, but I think it's more important you focus on these core scheduling techniques. And so we'll look at some basic concepts, scheduling and special scheduling issues, and we'll also include some real-time scheduling because that seems to be an important topic more recently, even though real-time scheduling has been a specialized topic, not usually included in OS. Recently, even mainstream OSs are starting to address real-time scheduling, so that's why we include it here. So the basic concept is that, well, you do scheduling when you do multiple processes, right? Multiprogramming. And in multiple processes, you at least on the uniprocessor, you run one at a time. And so that means even though there may be one or more processes ready to run, they may just have to stay in the ready queue for a little while and wait their turn to execute. Okay? And so how do you decide which one to pick and run at what time? Then that's the question of scheduling. Okay? So scheduling is really this decision to choose which process among those eligible to run to execute next. And so we need to come back to the notion of when a process can run versus when it has to wait, right? So you remember this concept of CPU burst versus I/O burst, right? So burst means it doesn't continue doing it for some time. So you could have long CPU burst or you could have short CPU burst. And so that the relative burst lengths of these I/O and CPU determines the characteristics of the program. So some programs are what's called I/O bound, others are called CPU bound. So that doesn't mean the program does only I/O, no computation, or only computation, no I/O. They're the mix, right? So I/O bound one has much more in terms of CPU bursts than I/O. Or I should say this I/O bound ones do more I/O than computation. CPU bound do a lot more computation than I/O. Of course, this is all relative speaking. And so the long and short, that's a relative term. But then in these programs, they tend to say, okay, well, on average, they're comparable in terms of the standard for what's short, what's long. So they don't really make much of a distinction there. So in the program, what you have is CPU burst, I/O burst, and when I/O is happening, tends to take a long time. So it usually then gets context switched out, and then put on the wait queue. And during that time, because that program can't do much else anyway, so the processor or OS switches context to some other program, run it for a while, and so forth. And then when the I/O is ready, okay, good. Then it then gets put back on ready queue. Then when that processor's turn, run it for some more time, right? So the goal here is really you don't want to waste CPU cycles. And at the same time, you want the different processes to get their chance to execute. And so these bursts, how long are they? So here's a histogram. Basically, they plot out how frequent each burst length is. So a burst length, these are in milliseconds. So anything 8 milliseconds or longer, their percentage is rather low. So that means it's almost negligible to have to deal with processes whose CPU bursts are longer than 8 milliseconds. Okay? So in other words, a process usually doesn't run more than 8 milliseconds continuously before it hits an I/O. Is that really true? Well, this is statistics. So, and this is particular workload. okay? But you can characterize, it all depends on what you're doing. And if you're doing a lot of number crunching, and in fact, the I/O actually include disk access as well, okay? So, so the idea there is, right, if you're doing a lot of computation, chances are you may need disk directly or indirectly. And indirectly means potentially it's a virtual memory kind of page fault and things, and then that involves disk as well, and that counts as I/O. But CPU bursts tend to be rather short, and of course it could also be a system call as well, right? So, so this means every 8 milliseconds or so, chances are another program gets to run, but you can't say no. Every program behaves like this. This is just a general trend. Okay, so most of them are on the order of like a few milliseconds. And so you don't want to switch too often. You don't want to switch too infrequently either, right? And so this, and of course, this depends on the processor speed as well. Okay. And for scheduling, one fundamental assumption, and we talked about this, is whether it's preemptive or non-preemptive. So the CPU scheduling decision can be made a number of times when a process switches from running to waiting. So, for example, performing an I/O, right? Then that's when the scheduler may need to make a decision, because that processor, the OS gains control back from the process. So it has to decide, okay, now I can't run this process because it's waiting for I/O. What do I run next? That's one opportunity for the scheduler to make a decision. Who do I run next? And also, like when the process switches from running to ready, when can that happen? Well, that's when the timer interrupt could come in, right? And then you context switch it out, and then you want to give some other process a chance. So that's another decision point for the scheduler. Or from waiting to ready, when is that? Well, that's when I/O completes, so the program can resume. It doesn't run right away. It gets put on the ready queue. Then when the scheduler comes, and then it may or may not pick that ready one, right? So non-preemptive, as we talked about the previous week, it's also called cooperative. That allows a process to keep CPU until either it has to wait for an I/O, or it terminates, or until it explicitly yields. But a lot of these APIs actually don't include a yield. So that's why the book actually doesn't include a yield in this case. But strictly speaking, if you use a cooperative threads package, yeah, you do a yield. Okay. Now, preemptive is one where the scheduling can happen in all four cases. In other words, whether the process goes to an I/O, or an I/O completes when it gets the timer interrupt. In other words, the time slices up, or when it terminates, right? So these are the points where a scheduler could come in and would need to make a decision somehow. Now, preemptive is desirable in the sense that it gives a processor, each process, a chance to run, right? Because you might run all you want, but timer interrupt comes in, grabs control back. The OS can give control to another process, let it run. So that is achieved with preemption, and that's a way to prevent a single process from hogging the entire CPU. And it does better with processor utilization, but it complicates things at the same time. What is it? Well, biggest problem is what's called race condition. Why? Because the preemption is done oftentimes in the form of an interrupt. And as you know, interrupt happens anywhere. In fact, the interrupted program might not even be aware that an interrupt happens, right? It is done with such nice abstraction at the hardware level. The interrupted program doesn't even know it got interrupted. It just keeps running along. But in the meantime, right, somebody between instructions could come in with an interrupt, save its state, handles interrupt, in fact, context switch, and then switches back, and the program just keeps running. It's nowhere in the program do you ever say, this is a point of interrupt. I only allow interrupt to happen here, there, there. Well, you might as well put yields in those places, right? That makes your program really messy, and it's really not the right way to do it. But to make it nice for the programmer, the OS has to do a lot of work to handle the race conditions. Why? Because if you're in the middle of updating some data structure and then you context switch out, even though the processor or whichever code can save and restore state, it only saves and restores those states inside the CPU, right? Your register set, your register file, whichever, right? The bank. But what about anything to do with shared memory? You've seen shared memory type of use, right? FIFO, right? And all that. If you do any shared memory, you actually could be interrupting a program in the middle of accessing that shared memory, right? And you say, what's the big deal? Well, by the time you come back, the other guy may already have updated the memory, and then you got restored into the state before you thought the memory was updated. And so you could override their changes, or you could update it in such inconsistent ways that it can mess things up really badly. And so this is the topic of synchronization, and that's going to be covered in Chapter 6. So you got to be very careful, not just do preemptive scheduling, but do it with synchronization. And that comes at a cost. But still, people think it's worth it to do preemptive scheduling plus additional synchronization. Now, so for preemptive and non-preemptive kernel design, you need to be aware of a number of things. Right? A non-preemptive kernel would then wait for a system call to complete or a process to block before the context switch. It's simple, but performance is poor because then the utilization is probably not as good. It's not as suitable for real time. For most real-time systems, well, but again, I must inject my own commentary here. Depends on what kind of real-time system. Real-time systems are not all the same, but this book is written from the point of view of a general-purpose OS person, as opposed to full spectrum of real-time applications. And in real-time systems, even they don't quite all agree on one way of doing things. But here, they're heavily biased towards preemptive scheduling, preemptive kernel. Why? Because for general purpose, you want to utilize the processors very well. But in real-time system, their goal really is to have predictable and reproducible timing results. And so if you have to pay a high price for, in terms of processor utilization, in terms of power, it may be worth it to them. Because it's better you spend a lot more cost, underutilize a processor, than to crash a car or crash an airplane, right? So the priorities are very different, but this is purely from the OS point of view. So they think preemptive kernel, and that's really the trend anyway in modern OSs. Creation could happen when making a system call, or when kernel is making critical changes. And so that's how you design the kernel, okay? And to do preemption, you need to do synchronization structures, such as mutex, such as locks, such as semaphore, monitor, and a bunch of those. We'll introduce those in the chapter on synchronization. So interrupts. So interrupts could come in any time. So one way to implement these synchronization primitives is to say, well, I really don't want interrupts in this case. Let me be sure I do this. Nobody should interrupt me. Let me complete this all or nothing. So that's called atomic operation, okay? All or none. And this is one very strict way of implementing what's called atomic operating by temporarily disabling interrupts. So on 8051, you can temporarily disable all interrupts and re-enable all the previously enabled interrupts by setting the EA bit. Disable all of them off, but you still remember which ones were on. By turning on EA, those, so essentially a mask that's ended with all the enabled interrupts, right? And then all of the previous enabled ones are now re-enabled. So that's how 8051 supports temporarily disabling and re-enabling. Now, interrupts shouldn't be disabled for too long for obvious reasons. Why? Because some interrupts are transient. They are not like coming in with a buffer. No, some of them, they're there, and then if you don't catch it within some window of time, they're lost, as if the interrupts never came. Okay? So what are those? And if you look at 8051, they'll tell you, look at different interrupts, they actually behave differently. So a UART, for example, there's a buffer associated with it. So when interrupt comes, well, that buffer remembers that the bit is set, that bit sticks around. But you can't disable for too long, because if you wait for too long, another byte could come in and override that buffered, right? And so you only see one byte as opposed to two. There are some interrupts that are tied to lines. There's no buffer behind. What would those be? So for example, if you use a button, right? That's actually, when you press a button, usually that's pull down, and then release, that pulls up. And in fact, several devices may share the same interrupt line. Okay? So they may request an interrupt, but then they only hold that for so long. And if you don't come around in service, it actually could be gone. Okay? So you really shouldn't disable interrupts for too long, because you could lose important interrupt events. Hopefully you would disable only for a couple instructions, not for much longer than that. And even ISRs themselves shouldn't be too long for the same reason. Why? Because interrupt service routines may have priorities. So yes, you could have nested interrupts. A lower priority, handling a low priority interrupt, a higher one can preempt or interrupt that lower priority interrupt. It could be nested. But what if you're handling a higher priority interrupt? Well, the lower interrupts couldn't come in, so that's a lot like disabling those lower priority interrupts, right? So you really shouldn't write your ISRs that are too long. Now, here's another important distinction between dispatcher and a scheduler. So we've been talking about scheduling. So, but really there are two parts. One is the part that makes the decision. And one is the one that actually executes that decision, right? So the one that actually does the switching, whatever process to context switch in, switch out, that's called the dispatcher. And the one that makes the decision, in other words, chooses which process to schedule next, that's called a scheduler. Okay, there's that distinction. Even though in practice, you might combine the two, because you make simple scheduling decisions, or you always hardwire or only do one or two policies. But the scheduling policy could be very involved too, and you might want to be able to decide different kinds of scheduling policies, which we'll talk about, right? So that should just be some code to make the decision. But the dispatcher is the mechanism that does the context switch, right? So the dispatcher shouldn't care which scheduling policy or how you arrive at picking the next process to schedule. It just says, whatever decision to me, just somebody decides. Tell me and I'll do it, right? So that's what a dispatcher does. So dispatcher does saving, restoring state, a lot like we talked about for that ETSIM little threads package, right? Whether you're doing preemptive or cooperative threads, and then jumps to that process that's scheduled next. Now, a scheduler is the one that does the choosing, right? That determines which one to dispatch, and even when to dispatch. You could even do scheduling for some time in the future or at some point in time, and that is something that a real-time dispatcher can do. So it may make the choice, but not necessarily say for the next one to do. I have to pick one right now. Just one is blocked, and let me pick one. Well, you could do that, or you could say, let me plan it out. Right? Some things may be associated with the time, and at that time, yes, I do dispatch. Right? So the scheduler would then determine not only which process, but also when, potentially when. But with real time. That's for a lot of real time, but for general purpose OS, most likely all you do is pick the next one, right? And then maybe already lined up in the queue, so that would be easy. Anyway, so you need to break down the latency in terms of the amount of time it takes for the dispatcher to stop one process and to start another one, and as well as the scheduling time, because people care about the overhead incurred by the kernel, right? And scheduling often is done in the kernel, and that means you shouldn't try to always do like the optimal scheduling algorithm, which could be NP hard. That means it's taking exponential time. It's all it's doing is picking the optimal one, but it takes exponential time. So that means you're just stuck in the kernel, not just picking one process. That's not worth it. So you got to limit yourself to very efficient, very short amount of time in your scheduling decision, right? Your data structure also matters. So that means oftentimes, yes, you could do much better, but if you have to do it online, better limit it to very, very simple ones that can be done in hopefully bounded delay, if not minimized, right? So now this interrupt re-enabling time, usually that's a couple instructions, if not just one or two. Context switching time, so saving state, restoring state, jumping there. Okay, so let's take a look at scheduling algorithms. Now, before telling you about scheduling algorithms, you need to know the criteria, right? So what do people care about? So people care about a number of different things. One is CPU utilization, one's throughput, turnaround time, wait time, or waiting time, and response time. These are the 5 primary things people care about, okay? And so you could say these are the cost functions or maybe objectives for these scheduling problems. And CPU utilization for sure is important in that basically it's defined to be the percentage of time when the CPU is not idle or doing work, right? And so ideally 100% utilized, but is that really a good idea? Well, it depends. Right, so in practice, 40% utilization is actually pretty good. Or it's a light utilization. 90% would be heavy. Getting to 100%, I mean, it might actually be counterproductive. Depends. And for mobile processor, you probably know, if you do lots of things on your smartphone, then you could burn your pocket or burn your palm, right? Or catch fire. Because mobile processors really are counting on you not utilizing your processor 100% of the time. And so that means CPU utilization is certainly one of the criteria, but not the only criteria, right? It could be power, which is not listed here, but we will mention this a little later. And throughput is one that, especially if you do batch processing, that you care about. So that's the number of processes that you complete per time unit. And of course, this is over a long period of time. This is more of an average. Okay? Turnaround time is from the time you submit a job or process to the time you get it back, completion, right? And so that's turnaround time. It's different from throughput, just because different jobs have different lengths, right? So, and so when you average out, it may or may not be skewed by the average. But the individual turnaround time is also important. Now, waiting time is the total time that a process is in ready queue rather than running. Okay, so don't let this term mislead you. Just because it says waiting time doesn't mean it's the time is spent in wait queue. No, wait queue is for I/O. This is waiting in ready queue. So that means it's supposed to run if nobody else is running, but somebody else is running. So how much time are you running somebody else's process instead of the one you want, right? So now response time is the time from submission to the first response produced. So that's kind of a funny concept. So it doesn't mean the time completed. Why? Because some programs it only cares about like event response to event response as opposed to completion. So for example, I'm editing something. I'm actually idle a lot of the time. I don't even know when I'm gonna quit, right? So, but then I care if I hit a keystroke, click a mouse, or something that the computer has an indication saying, yes, I got it, and then working on it, right? I copy and paste. I don't want to wait 20 seconds only for it to paste and show that it pasted, right? I wanted to see that, yes, it's actually responding to my request. So objectives means you want to maximize or minimize these criteria, right? Or you might say cost functions. So you want to maximize, oftentimes you assume you want to maximize CPU utilization, you want to maximize throughput, but minimize turnaround time, waiting time, response time. Okay, so these are the commonly assumed objectives, okay? So scheduling strategies, they go from some really simple but not working so well to some really good, optimal, but not realistic. So somewhere you have to approximate and you rely on heuristic or approximation, estimation, and so forth. And then there are these schemes that are kind of general frameworks for talking about scheduling in general. And also variations, combinations thereof. The first one is first come, first scheduling. That's kind of intuitive. So like a scheduler sitting there, I'm not doing anything. Somebody has a job. Oh, okay, take it, run it. And then runs it and runs it. And another job comes in, right? Think of it as in those old days, submit a deck of cards. And then it starts running. And say, okay, you wait. And then the next one comes in, okay. And then it just have to wait in line. Kind of fair, right? That's first come, first serve. So by default, first guy just runs until completion. And the second one that came, of course, they had to wait, right? And then submit them, start running them until they finish. And then third one, which may have already arrived, and then do that, right? So that's the most straightforward way, of doing scheduling. So by default, you assume it's non-preemptive, right? So seems fair to me, but what's wrong with this? Well, in practice, you're likely to get into the case of long wait time. You've probably seen this at supermarket checkout, right? So like I have just like 1 or 2 items. I just want some candy. And then there's this guy with a big cart, like the 2 carts of like, I don't know, they probably want to stock up for a typhoon or something. A big cart in front of me. And I just happened to one step, oh shoot, the guy just got in the line before me. Okay, fine, I just wait. And wouldn't it be nice if I said, could I please cut in line in front of you so I can get on and do my thing? You're gonna have to wait that long anyway, right? So you've seen this case, right, at supermarkets or checkout line. So first come first serve would have that kind of problem where I'm the little guy with just one candy to buy, and the guy in front of me big cart, and that's gonna take them 10 minutes to check out, right? So then if I'm just off by a little bit, I arrive just 1 second later. I end up having to wait their entire time, and then before I could pay, right? So that seems like it has that problem, as this Gantt chart shows. So it really depends on the order of arrival. So in this first case, right, this P1 is here, and then it takes a long time. P2, P3 are relatively short. They end up waiting for this guy to finish their checkout, a big shopping cart, before they can buy their candy. Okay, so that you make 2 guys wait a long time. Is that worth it? I mean, yes. In the end, the CPU amount of time is the same. CPU does exactly the same amount of work, but the experience is so much worse, right? You piss off 2 guys there, just one candy, right? Compared to this other way. Now, so if you can know that, okay, then if it was the case where P3 could be scheduled, or P3 just arrived or maybe just cut in line, or then they get to check out, P2 gets to check out, and then P1 runs next. Then and then it's much better experience for P2 and P3. P1, I say, oh yeah, I actually waited a little longer than I needed to, but then I waited a long time anyway, so I waited 4 time units instead. So that's waiting time is the time you're ready. I'm ready to pay. I'm ready to check out, but I have to wait. Right? Wait in queue. Right? So it's simple, seems fair at some point, but it's bad because it's dependent on the order of arrival, and also the CPU-bound and IO-bound processes don't mix very well. And that is really just another case that is similar to this, because they could arrive and they could run a long time, but then naturally you get into a case like this, and that's called convoy effect. What's a convoy? Convoy, as you know, important like president or some emperor, or not that many emperors anymore, but important guys. Big team, big cars with like decoys and like the guards and heavily right. So that means the big fish has to go by first before the little fish could. So little guys would have to wait for a long time for the big guys. So and so that could lead to low CPU utilization, especially when you have these mix of I/O. And also, it's effectively non-preemptive. Yeah.
How can you calculate the CPU utilization?
Okay, so you'll see in the sense. Oh no, I don't have an example here. But what happens is then you have these I/O-bound processes in there, and so that if it's non-preemptive, then that means these other guys can't even come in. Okay, so. So that means you have to run them till completion, including waiting for their I/O. So that's poor CPU utilization. But preemption can fix that. Okay. And so one other fix is to say, well, seems like the guys with the short item list or just wanted to buy candy, you should let them go first, right? And so that's shortest job first. So that says the processor or the OS gets to choose the process with the shortest next CPU burst. Okay, but a lot of our examples here are only just to the next burst. And what happens after that, don't consider. Okay. Now, shortest job first really is more of a misnomer because it's not shortest total job length. It's the total next CPU burst. In other words, the CPU burst until you have to do I/O, right? And that's when you have to wait. So now, shortest job first is optimal for minimum waiting time. But that's assuming you know the next CPU burst. But in practice, you don't, and I'll explain that. But for now, let's just look at and shortest job first actually has two schemes. One is preemptive, one is non-preemptive. So in the preemptive one, it's really the shortest remaining CPU burst first. So when a new job arrives and you compare its next CPU compared against the remaining estimated CPU burst for all the ones against the current running one, right? And whichever is shorter, you pick it, right? And if it's shorter, the new guy is shorter, preempt the current one, run it. If it's longer, then you keep running the current one. Now, non-preemptive version, basically, you have to run a process till its completion. And even if a new job comes in and then has, hey, I got the short one. So this is more like at the time of admission, right? So the checkout line is more like the non-preemptive one, right? Because in the middle of checking out at the cash register, you really can't do another because they're halfway printing their receipt. You can't just you can't just check out cutting into the middle of a person who hasn't finished their checking out, right? So the supermarket case will be more practically implemented in the non-preemptive case. But when you're in line, you haven't started the checkout process, then yes, that's when you can reorder, right? So that's how you would do it. And so how do we know the length of the CPU burst? Well, you can't, because it's an undecidable problem. Anybody knows what undecidable means? If you ever taken theory computation, you know a class of problems are undecidable in the sense that you can't really definitively say it's gonna, halting problem is one. So I give you a program, you can't always tell if it's gonna halt. If it halts, it halts, but you can't say it doesn't halt. And so it's undecidable. It's worse than exponential in that exponential, at least you know it eventually finishes after exponential time. Undecidable, it might not even finish. So you can't definitively say. And so estimating CPU burst is one of those problems, right? So what do? You gotta then predict it. I'll guess it. Okay. But anyway, for now, let's assume we have way. So non-preemptive case. So we have the job mix 7, 4, 1, 4 as the burst time, and they arrive at different times. So 0, 2, 4, 5. If one arrives, you serve it, right? That's the only one. No decision need to be made. And then in the middle of doing this 7 unit checkout, I guess, then at time 2, the next guy, P2, arrives. 5 items in this cart. And then, but it can't do. So it has to be queued up. And then at time 4, task P3 arrives and can't make progress. So once you start P1, you have to finish it first. Okay. So after and then P4 arrives here at time 5. Now at time 7, P1 finishes its 7 item checkout. So the cash register is ready to pick the next customer. So who would this pick? Well, so this is the non-preemptive one. Well, so in this case, you can see what is it? P3, right? Because P3 is only one burst time unit remaining. It's the shortest one. I just have a gum. I don't know about. Okay, so then, yeah, here you can come, and then the cash register picks the guy with just one candy, and then even though P3 arrives later than P2, so essentially let P3 cut in line, right? And that's one item. Okay, you're done. Then now time unit 8. The processor or the CPU or the OS has to pick between P2 and P4. Now that's kind of a tie in that because P2 and P4 both have burst time of 4, right? So to break this tie, you could go to arrival time because you both have 4 units, but then P2 arrived earlier, they should go first, right? So that's one way you can do the tiebreaker. Okay, and then finally P4 gets to execute at time 12 and to completion. So the response time will be waiting time before you can run for the first time. So it would be 0 for P1, 6 for P2, 3 for P3, and then 7 time units for P4. Waiting time, if you do this adding, right? So that means by the time they arrive, ready, but then have to wait, right? So that would be 16 time units. So divide by 4, average waiting time is 4. So this is for non-preemptive. Now preemptive means once you start executing a task, in the middle of it, you can actually preempt and then let somebody else cut in. Okay, and so this wouldn't work in the case of cash register checkout, but then it works in other cases. So same task mix, but then the P1 schedules, and then it thinks if nobody else expects to execute, it can do 7 time units. But then by time 2, P2 comes in, says, "Oh, I only have 4 units of work to do," but P1 has 5 remaining units, right? The 2 out of 7. So says, okay, fine, P2, you get to go ahead. And then P2 does 2 units, and then, oops, P3 comes in and say, hey, I got 1 unit of work to do. Okay, I get to go first. So P2 says, okay, fine, yeah, I have 2 units, but you are shorter, so P3 gets to execute. And of course, when these get preempted, they have to wait, and so that means they're in this pink or salmon color. And then P4 comes in, it says, oh, I have 4 units of work. P1 still have 5 units of work, but P2 now has only 2 units of remaining work. Okay, so P2 gets to run. And then between P4 and P5, well, P4 has 4, so that means 1 less unit of work to do. So P4 gets to run, P5 gets to run. So yeah, I mean, so P1 is kind of unfair because it actually waited for these other guys for a long time. But then for P3 came out not having to wait at all, and then these other ones waited a little bit. So that means the wait time, the P1 gets penalized for a longer job, but then okay, fine. And in the end, do you win this way? Yes, if you do the math, right, then it actually the average works out to be 3 instead of 4. Okay, 4 it would be non-preemptive. 3 it would be the preemptive one. So, but then of course, average could be misleading. Okay, because it gets skewed by one of the outliers, and so that doesn't say anything about the worst waiting time. And sometimes you do have to consider the worst waiting time. Yeah.
那这样的话，那个 P1 不是中间就是有一段时间都没有处理。
Correct. And so this is not necessarily the best policy. It only says in terms of optimizing for total waiting time, this is the best. But that might not be best by all criteria. Okay, only one of the criteria. Right? So yes, there are better ways, and that round robin could be one, or aging or something else could also make it fair for everybody. So this is only considering total or average, which really, I mean, you gotta be more careful. Anytime you say total or average, right? I mean, what's a distribution, right? So distribution matters too. So to be fair, what does it mean to be fair? Well, there are many ways to be fair. Right? So putting some bounds on it, I think it'd be more fair. Right now, there's no bound on the worst case one. So P1 gets penalized a lot that way. But in the end, yeah, average kind of is better, right? And it's probably the best overall average you can achieve, but then that may not be what everybody wants, right? So now, shortest-job-first, strictly speaking, is only a theoretical scheduling algorithm, because in practice, you don't know for sure what the next CPU burst is. You could analyze the program all you want. Yes, in some cases you can decide, but in general you can't. You don't know when the next I/O is going to be, especially if it's the case where it runs until user hits a key. Otherwise, it's busy and indexing and checking spelling and then try to fill in all the work in whatever it wants. In general, you don't know. So what can you do? Well, you could do approximation by prediction. And so here's one of the formulas used for prediction. It's exponential running average. So that means you have a weighted average, and then the weight is exponentially decaying for older time, and you give more weights to the more recent time. Okay, so basically you have history, and then these are represented in terms of these variables here, and then the weight would be like you have some alpha. Alpha is a fraction or between 0 and 1, and then you weigh it. So if it's 1/2 for the most recent, and then 1/2 squared would be what? Then 1/4, 1/8. So you attach a weight. You scale the weight of the time relative to how recent it is, right? So if it's really old, it really hardly carries any weight. But it's most recent, it carries more weight, right? That's all it is. And so by summing it up, then you kind of smooth out the curve over time.
就是说，以后就 就是越久了之后，那个它预估的时间那个差会越来越小。
They carry less weight. So here's an example. So you have the actual CPU burst versus the guessed time, right? So initially, well, you don't know. You have to make a guess. You have to start somewhere. So you may be way off. But then after applying that formula, right, there's not much history, but then you put more weight, so it's converging, and then, wow, okay, after a couple of times, you actually hit right on. And then if this changes pattern, okay, then it takes a little bit time for it to catch up, and then it dips. But then suddenly it changes characteristic. Okay, it's going to take a few cycles for it to converge to the new pattern. So, but it's trying to follow your recent history. Use your recent history as a way to predict your recent future or upcoming immediate future, right? That's all it is. And that's not the only formula. You can have many other formulas, so hopefully doing a better job. But then it's all prediction, right? So you have to apply some additional knowledge as to the workload mix. Or are you doing multimedia? Are you doing what kind of workload? And that may help you make better predictions. So round robin is another common scheduling algorithm, and we talked about round robin also. Basically, it says everybody takes some turn, so nobody gets to wait for too long, right? Everybody makes progress. But to do this, you have to make assumption that it's preemptive. If it's not preemptive, what happens? It's essentially first come, first serve, right? Because it's not preemptive, you let it run to completion. So how do you decide what's the incoming order, right? First come, first serve. So round robin, to be meaningful, has to be preemptive, right? It assumes preemption so that it can give everybody an equal share of time slice to execute, so that they make progress. Not necessarily proportional to their execution length, but because you don't know in practice just how long it's going to take. But you at least take turns serving everybody, so they all get attention, right? So they all make progress. And the reason for this is there's no starvation. In other words, you don't necessarily penalize everybody. So in other words, the wait time is going to be limited to the number of processes, right? But at least nobody waits longer than a number of processes. It's multiplied by your quantum. So quantum is this basic time unit or time slice. And in practice, this is anywhere between 10 to 100 milliseconds. Probably 10 because you've seen the job mix or the distribution, the histogram earlier, right? So in other words, you can imagine, right, a timer interrupt associated with this. So every quantum timer interrupt kicks in, and then that's when says, okay, I don't care if you have much more work to do, somebody else gets to run. Preempt that, runs the next guy in turn. So they come in a circle, right? So if you run, then you gotta wait your turn, right? So next guy, and then in a circle, okay? Now, so in round robin, the quantum size matters, right? Because we said about 10 to 100 milliseconds, but who's to say, right? What if I want to do the round robin once a second, or once every 10 seconds, or, right? Well, what's the right amount? Well, I mean, these are really tuned for a number of issues. One is really with the absolute performance of the CPU. The other is with the user experience, right? So these were picked during the time when you were doing a lot of these terminal type of processing. So in other words, dumb terminal keyboard, you type a key, and then goes straight to the machine, and then it needs to come back with a UART to display whether your cursor moved or which character you just typed, right? And users can't type that fast, but then users do want some amount. And recent ones, I mean, you have multimedia, you have like voice over IP, and there's that latency. And even for telephones, a latency of like 10, 20 milliseconds is probably you can start feeling that delay. So that's how some of these latency got picked. Part of it is really the practical time due to the application. But if the time quantum is too long, then it starts behaving kind of similar to first come, first serve, right? But if the time quantum is really small, yes, you switch very often, but then context switching is not for free. It takes time. Saving context resource, saving context, and if you're doing too often, it's like, hey, I just did the context switch, now I have to switch to another one. So you can't amortize that cost over long enough execution or long enough CPU burst. So that's a bad one. So there's only practical guidelines, but again, you got to do this both in terms of CPU's performance level and also the application kind of application experience you want to deliver.